Good morning, everyone. Xin chào. So, I heard that many of you have just finished taking a course in statistics. Is that correct? Okay. For those who have taken statistics, please raise your hand. Okay. So, this course that you have taken, is it a undergraduate level statistics course, or is it a graduate level course, or is it focusing on biostatistics or general statistics? General statistics. Okay. So you have learned about standard deviation, 95 confidence intervals, t-test, and all that. Okay. So in the statistics course, what kind of tests have you been taught? Give me some examples. Oh, you know the SPSS. That's great. Okay. So I would be talking a little bit about the SPSS. Okay. So I guess many of you are taking this course for the first time. You were not here last year. So let me take this opportunity to introduce myself. Okay. My name is Yeung. I was born in Hong Kong, so Chinese and Cantonese my first language, and I went to the United States for college, and then PhD, and then MD, and then went through the residency training and fellowship training, and then become an assistant professor at MD Anderson, and I've been at MD Anderson for the past 17 years. And so I belong to two departments. My clinical activity is primarily in the Department of Emergency Medicine. I see patients in the emergency center of MD Anderson Cancer Center. I also have a training in endocrinology, and I have a joint appointment in the Department of Endocrinology and Hormonal Disorders. And I do research focusing on the connection between endocrine diseases and cancer. And some of the main research topics that I've been working on are the impact of diabetes and obesity on cancer, as well as cancer metabolism. So today, we have a very general topic. We're just talking about some basics about biostatistics. And what we're going to do is to have an overview of how to use statistics in biomedical research. Because I'm not a mathematician and not a statistician, so I'm not qualified to teach you about statistics. But I have used statistics a lot in the course of my research, and what I'm going to do is to give you some pointers or some tips about how to use statistics in scientific pursuit. There you go. Okay. What did I do?
Just prop out. That's
Okay. So, and the acknowledgement, we would like to acknowledge the VNU Education Foundation for the funding to make this happen.
yeah, just touch it.
Okay. And thank the cooperation of the VNU and the University of Sciences in Ho Chi Minh City, and of course, thank our support from our parent institution. So as a disclaimer, I am a physician scientist and not a statistician, and I'm just giving you the perspective and preferences. So as an overview, this is not in any particular order. So this is what I'm going to try to accomplish today, is to talk about some basic statistics concepts, some common analysis methods, and some common flaws and mistakes that you would even find in the published literature. So many times there are mistakes in the manuscripts, in the papers, and if the reviewers didn't catch it, then it will slip through and it will be published. So don't believe everything you see in the published papers. And also within the presentation, I will talk about some of the my own preferences about graphical presentation of data. So, what is medicine? Medicine, involves doctors seeing patients, and then behind that, there's all sorts of technology that would help the doctors to make the diagnosis and as well as treatment, and all this, are based on knowledge. Okay, so this is the timeline or history of the Western medicine. Back in the old days, so-called Western medicine, or the medicine of the Greek people, was not much different from traditional Chinese medicine or traditional herbal medicine. It's all based on the experience of people, how to manage the diseases or trauma or knowledge of the land, knowledge about the plants and the animals and substances that can use to help to heal illnesses or injuries. But over time, the difference is the attention to details in terms of the human anatomy, and then as the knowledge increase, what I think it's the last part here, the last 100 years, that make the Western medicine and Eastern medicine to diverge. And Western medicine is based on the scientific method to test knowledge, to find new knowledge, and whatever that the physicians need to do need to be based on facts, based on evidence. And so over time, people have been talking about medicine as both an art and a science. So this is very distracting. I'm going to unplug this. So, in terms of the arts and humanities, the patient and doctor relationship is a human relationship. There's not much science between them. And there's the rapport between the patient and the doctor, the ethics of how the doctor conducts himself or herself, and the empathy that the physician feels, and then also the practice styles and the caring that the physician provides to the patient. And the first role of the doctors is do not harm. And many of the doctors take the oath of Hippocrates. Hippocrates was considered the father of Western medicine. And I went to a medical school that all the graduates took the oath of the Hippocrates to affirm the ethical standards of the physician. And there's also the Helsinki Declaration that in the course of finding knowledge for medicine, for clinical research, we have to respect the will of the patients, and this Helsinki Declaration basically underscores the ethical standards for the conduct of humankind and research. So, for the science part, the bedside diagnosis is based on signs and symptoms, and behind that, there's this based on the physiology and pathophysiology of the diseases. And the diagnostic test, the imaging test, and the biochemical test, all these are based on science. The clinical management, okay, the medicines we use, what treatment is the best, all these are also based on clinical science. It's based on clinical trials. And that's what these days, what we call the evidence-based medicine. How does this evidence come about? It's all based on statistics, all based on clinical trials. We randomize, we test, and we see if it's real or not real. Now, in the medical literature, this called grades of recommendation, assessment, development, and evaluation. So basically, this assesses, evaluates the quality of the body of science behind or body of evidence behind a specific clinical recommendation. So we evaluate the within study risk of bias. What are the methodological quality of the study? Is this the directness of the evidence? Is this an indirect evidence or direct evidence? Whether there's heterogeneity, whether some studies say yes, some studies say no. What is the precision of the effect that are estimated and the publication bias? And many of you, if you're in research, you will know that only the studies that are positive are likely to be published. The negative studies do not get a chance to see the light of day. So, therefore, in the evaluation of the evidence, you have to be aware that there could be a potential of risk publication bias. And in fact, there are statistical techniques in the meta-analysis to analyze the probability of this type of bias being present. So, using all these methodologies in evaluating all these quality of the evidence, and then you would grade the evidence, grade the specific clinical recommendation, whether it is high quality, meaning that it's substantiated by randomized clinical trials or double upgraded observational studies, and then the next level of quality is like downgraded randomized clinical trials or upgraded observational studies, etc. And then when there's very low quality, there's very little scientific literature or clinical trials to support such recommendation, it will be called, it will be based on case series or case reports and downgraded studies. So for clinical medicine, in order to get all this evidence, okay, everything is based on science. So as clinicians, or as well as scientists that are going to do research in biomedicine, everything need to come about using the scientific method because we need to test and measure without bias. Okay? So the person that is doing all this must have integrity, honesty, and the commitment to seek the truth. So this is my personal algorithm for the mechanics of how to find out about the truth. So in science, we have to read and we have to study. Otherwise, we don't know what we're going to do. How do you know what experiment you're going to do? How do you know? topic you're going to choose. So you have to read the background knowledge and understand what is at the cutting edge. Okay? What you do, it's not important, and nobody cares about what you do. Even if you finish your study, you cannot publish it. Nobody cares. So you have to know what is the frontier knowledge. Okay? What matters. Okay? And then you commit your effort. Okay? Otherwise, you're wasting your time. So with the background knowledge, okay, or you have some important observations by chance, then you come up with a question. So all the scientific research is to start with a question. What is it that you want to know? Okay, and from that question, or you a hypothesis that can explain the observation. Okay, and then based on that hypothesis, you design an experiment to test that hypothesis. Okay, so and then from the experiment, the results of the experiment, you come up with a conclusion. Okay, so here are these steps: the observation, hypothesis, experiment, and conclusion. These steps that are highlighted in red. This is the main parts of the scientific method. Then how does logic and statistics fit in between? So this is where it comes about. So when you do the experiment, when you design the experiment, you have to test population or target population. And from that population, you take your sample. Right? From your sample, you do your experiment, whatever the experimental variable is going to be based on your design. And then you obtain your data. Then you analyze your data. Okay? And then from your data, you create your model, okay, to explain the data. And this is called deductive reasoning, deductive statistics. And then from your model, okay, you can predict things. And then you can test again and see if your prediction is correct. Okay? So from the reality to come to the conclusion, this type of induction or logic is called inductive logic. From your model to deduce the consequences, and that type of logic is called deductive logic. Okay, so from your conclusion, okay, you do your statistics and evaluate how reliable that is. Okay, so in general, in science, we accept the probability of being wrong as 5%. That means usually we are 95% sure. So with that, we move on, okay, and we consider that as new knowledge. And when the knowledge is proven to be true time and time again, then we accept that as the law of the universe. So where is statistics needed in biomedical research? So there are many types of biomedical research. Okay, benchtop experiments, animal experiments, retrospective clinical studies, clinical trial, literature review. Okay, so in all these different types of research enterprise, statistics is a very important ingredient in it. For example, in benchtop, when you're talking about whether something is different, to evaluate the differences between two groups in quantitative measures, or evaluate differences in qualitative measures, or whether two variables correlate with each other, or whether between the two groups, many different variables, are they different from each other, and which one is different and which is not different. And in animal experiments, and a lot of times especially in cancer research, we're looking at the differences in the growth rate of the tumor. So then we look at growth curve analysis. Okay, if we look at how soon the animals would die, okay, then that's analysis is called time to event analysis. And many times, even before we Okay, we have to write out the protocols and plan the experiment. In planning the experiment, one very important question is how many mice am I going to need? Okay, sample size calculation. Okay, so you do not use statistics to calculate the sample size. Okay, you may end up using too few animals, and your experiment has no statistical significance, and you ended up wasting the life of all these precious animals. Or if you use more than enough, too many animals, okay, so you're also wasting the life of these precious animals. So, as I, it's best to use statistics to plan ahead of time to do the experiment right and do it once instead of wasting. Now, in retrospective clinical studies, okay, we're very valuable. A lot of times, we to go back and look at the clinical experience to identify what we have missed or identify new hypotheses for further investigation. And many times in clinical studies, many variables need to be controlled. It's not like something else that is in the laboratory and that every variable is under strict control and you don't need to worry about them and only worry about your experimental variable. But in clinical studies, because humans are walking around exposed to many different things, different age, different background, different genetics, different gender, different race, etc., etc. So all these potentially complicating variables need to be controlled for, and there are statistical methods to control, to analyze multiple variables and see which one of these variables are significant contributors to the outcome variable that you're analyzing. So prospective clinical trials. Clinical trial design is very important. Okay, designing clinical trials is not much different from designing an experiment, okay? Except that some of the environmental factors will need to be controlled, and very often we would need to use multivariate analysis instead of some much simpler statistics. And you have to plan ahead of time that what methodology you're going to use to analyze your data. And from there, again, the sample size calculation is very important. Okay, you need to design the clinical trial in a feasible way because clinical trials are very expensive and it takes a lot of money, and you cannot afford to either design a trial that has power, then you're not going to get a statistically significant outcome or wasting too much money. So another way is to, after clinical trials are published, okay, you want to see what is the overall trend, what is the overall level of evidence, how strong that evidence is. And then you can search the literature and do analysis on the published literature. So this is a list of some of the common types of statistical flaws that you can easily find in the literature. Very often there's probabilistic study design. There's also application of specific statistical tests that are problematic in the literature. One major thing is the application of students' t-tests in the setting of multiple groups. Okay, so you all have taken statistics. Okay, you learned about t-tests. Okay, what are the assumptions in t-test? Anybody? The assumptions in t-test. What did we assume when we do the t-test about the population? Any volunteers? Okay.
I think that the assumption of teachers is the mean of two and not make sense when
Okay, so the other thing you're talking about the null hypothesis. Okay, the null hypothesis, when you do the t-test, is that the mean of the two groups are not significantly different. Okay, so when you do the test and p, if the p value uh, is less than 0.05, and you reject the null hypothesis, and then you say that the mean of the two groups are statistically significant with the probability that with 5% chance that you're wrong. Okay, so but that's not still not the conclusion of the t-test. Okay, so the t-test was designed based on the assumption that the distribution of the data in the population is a normal distribution. Okay, so if the distribution in the population, in the test populations is not normal, then t-test is not the correct test. Okay. And we also, when the t-test is designed to compare two groups, okay, when you do the experiment, when you have multiple groups, okay, let's say you have a control group in this experiment treating uh, the experimental groups with drug A, another one with drug B, and another one with drug C. Okay. Is it correct that I apply the t-test to compare the group treated with drug A with the control group? Okay. And then I use the t-test again to compare the group that was treated with drug B with control group. And then do it again with the t-test comparing the group that's treated with drug C with control group. Is that the appropriate test? No. So if you if you design and have done the experiment with multiple groups, okay, you're not starting out with two groups, and the distribution of the uh, sample in this population is not random. So what you need, I mean, this is a very common mistake. Application of student t-test when the sample distribution is not, or applying this test when there are multiple groups. And there's also the issue of multiple testing. Okay? So you have two groups, but you're testing for everything under the sun. So, for example, you have the control group, and then you have a group of patients treated with drug A, and then you're testing for hemoglobin, glucose, sodium, potassium, fluoride, everything. You have a long list of things that you test. Okay, so when you're comparing whether any of these parameters that you test and whether they're different between the two groups, is it appropriate to use the t-test? Yes, but is it appropriate to use the alpha of 0.05? That means should you only reject the null hypothesis with a probability of 5% chance being wrong? No, you need to correct for the rate of false discovery. Because if you flip the coin multiple times, okay, the chance of getting a hit would change. So there's also the presentation of the results is a very common mistake that I would go into a little later. So in statistics, the most important thing is randomness. Okay? So when you do your experiment, or you assess, evaluate, or design your experiment, and then you evaluate the data, you have to evaluate whether the results are obtained randomly. But randomly does not mean that you haphazard, okay, or unplanned or incidental. Now, allocating patients to a treatment group on even days or to the control group on odd days is systematic, and it's not random. Assigning patients with odd medical record numbers to the treatment group or even medical record numbers to the control group is systematic. Okay? And it's not random. Okay? So random refers to the idea that each element in a set has an equal probability of occurrence, like flipping a coin, provided that coin is a true coin and it's not a fake coin with both heads on each side, on both sides. Or rolling a dice, okay, and that dice is not loaded with lead or loaded with mercury. Random number generator, okay, and a lot of times with the advance in computer science, and many we use computers to randomly generate random numbers, and this is a very good, reliable way of random assignment experimentation. Now, I guess everybody uses a spreadsheet. We usually use Excel, or there are many other spreadsheet programs that are free as well. But the bottom line is the spreadsheet is a very powerful program, and very often we use it to collect data and then tabulate the data. So with Microsoft Office 2010, the spreadsheet has a limitation of about 65,000 rows by 256 columns. Okay, that's a whole lot of data. Okay, but usually, in everyday applications, that's very adequate. But in these days, when we talk about metadata, so a lot of times some of the databases would even exceed that. Okay. So it is good practice to keep the variable names in the first row, okay? Because in this program, you can freeze the first row, and then while you're scrolling through the rest of the spreadsheet, you can have a clear view of what the variables are. And to facilitate the transfer of data and compatibility of other computer programs. Okay, so it's a good practice to keep the variable names short and with no spaces. Okay. So this is because of compatibility issues with the variable names of some of the older programs like SAS, etc. But SPSS, it will automatically put an underscore if there's you have a space. But with the older versions, it was a significant issue. So with the entry in the box should be a number or a string of characters, and they either represent the quantity of a quantitative variable or a category of a category variable. Okay. So to make this spreadsheet easy to read and easy to analyze, we would try to use as little text as possible and use codes for the category. Like for example, use 1 to represent a male or 2 to represent a female. Okay. So in order to keep track of what you are using, what you're using to represent what, okay, it is very useful to keep what we call a data dictionary. Okay, so meaning that, like for column A or column B, which represents the sex of the patient, okay, You use 1 to represent male, 2 to represent female. Okay? So this is a dictionary, a notation of what your codes mean. And keep the free text comments away from the data fields. Okay? If you type in your comments in the data field itself, that would be a nightmare for the person that is doing the data analysis, because you cannot just cut and paste the column and cut and paste the boxes into the fields, into the computer programs for analysis. You have to clean up, get rid of, convert all the text to numbers or to the appropriate notations before you can do the data analysis. And that sometimes it's very time consuming. Now, this is an example of the spreadsheet, what I call the good, the bad, the ugly. So this is an example of a good spreadsheet. Okay? So you can see here, you have the name of the variables on the first row. And then the data is coded uniformly with M for male, F for female, and then the age of the person. Okay? So the age of the person need to be, the unit has to be the same. Okay? If you code, if you put type in numbers, okay, one is 56 years, the other one is 1.67 months, then the person that is doing the calculation cannot use the formulas that in the spreadsheet for the calculations, and they have to do the conversions individually for each box, and that will drive the data analyst crazy. Okay, so for race, you simplify the amount of text. Okay, here you have a letter W to represent the white race, B to represent the black race, A to represent Asian. Okay, so this is you have to have a data dictionary to explain. You need to write down what each of the letters mean. Okay, and then within the fields, you minimize the amount of text that are in the fields. Okay, so this is the good spreadsheet. Okay, so this is a bad spreadsheet. So you see that you have M for male, and then now you get the spelled out the male. Okay, so imagine how this looks when you try to sort the name. Okay, then you have the male in all different places, and then you have the capital M and then the small letter M. Okay, when you sort this, these are all in different places. Okay, same here. Okay, you have blanks that use the left out, and you have different units. Okay, so this data is not sorted. Okay, and this is the ugly. Okay, so you have the first row with too much information, and then the color is too distracting, and then the information is all in different pieces in different places, and this spreadsheet is not sortable. It's very difficult to analyze. So in statistics, we have the different types of data and different types of levels of measurements. Okay? You have the nominal type of data, categorical type of variables like gender, race, or whether the patient is hypertensive or not. There's the ordinal type of data means that these are categories that can be ranked. For example, okay, for a smoker, what is the degree of smoking? The patient never smoked. The patient has a light smoker, a moderate smoker, or heavy smoker. Or if we refer to the stage of the cancer, okay, whether the cancer is stage 1, stage 2, stage 3, stage 4. Okay. So these are not continuous variables. Okay. So you're either stage 1 or either stage 2. There's no stage 1.5 or stage 1.75. There's no such thing. Okay. But these represent categories that can be ranked. So stage 4 is worse off than stage 3, which is worse off than stage 2, etc. Or the discrete numerical data, like for example, the number of cells or the number of patients. Okay, there's you cannot cut a person in half. You cannot have like 1.25 patient. You have one patient or two patients. There's continuous scale, the type of data, age, there's continuous scale, and blood glucose, optical density, fluorescence intensity, okay, like these measurements from experiments. And this type of data is on a continuous scale. So you have data and then you have the measurement, okay, but there's many ways to express it. Okay? So how did Usain do? Okay, you all know Usain Bolt. So Usain is the fastest man on earth. So, but when he run the 100-meter race or 200-meter race, okay. So how did he do? Okay. So there are many ways of describing or reporting how did he do. Okay. So if you use a domino type of data, you can say, or you can ask, did Usain Bolt come in first? Okay. So yes or no. So this is a category type of data, whether he's first or not first. Or you can use the ordinal type of data, asking in what position did Usain Bolt finish. Okay. If he finished first, then it's a 1. If he finished the second, that's a 2, okay, etc. Or put the data using a continuous scale or continuous measure. How long did it take for Usain Bolt to finish the 100-meter race? Okay. Well, he finished in 9.58 seconds. Okay. Or he could, or perhaps in his previous race, he finished in 9.6 seconds. Okay. So it's a continuous measure of the time that it took him to finish the race. So after you record your data, okay, you collected your data, you have your spreadsheet, right? So one easy thing to do is to sort it, okay, and then to look at whether there are any missing data, and check the lowest and the highest value for each variable, okay. So if, for example, if you see for the variable age, okay, you see that the range is from 1 to 177. Okay, obviously he's wrong. Okay, how can you have a person that is 777 years old? Okay? So, or if your data is coming from adults, can you have a 1-year-old adult? So, these are quick ways that you can do by sorting data to check the validity of the data and check for careless mistakes, etc. Check the total number of entries. Okay, if your sample only have 32 patients and you ended up with 34 lines on the spreadsheet, obviously something is wrong. Or you can do a histogram of the data and then check and see if there are any typographical errors or any data points at the extremes that are typographical errors that have occurred. And cross-check the variables to detect impossible combinations. Like for example, okay, if you have a variable is pregnancy and another variable is sex, okay, and you cross-tabulate that, can you have a pregnancy? That's not possible. So you can, for some of the variables, you can cross-check and see if there are sub-combinations that are not possible. Like for example, if you have a study looking at the patients in the intensive care unit, okay, so the medications to maintain the blood pressure in the people that are dying with subsidy, okay, they would not be given to people with normal blood pressure before the ICU admission. Okay? So things that you can check to exclude mistakes. So statistics can be broadly separated into two big parts, so-called the descriptive statistics and the inferential statistics. The descriptive statistics basically summarizes your sample and the groups, identifies patterns in data, and identify the outliers, and it would guide the choice of the statistics that you use in the inferential part of the statistical analysis. For inferential statistics, okay, it's based on the theory of probability to make inferences about the larger populations based on the samples. So it is used to determine the likelihood that a conclusion based on the data from the sample is true or not. This is a screen for one of the programs that I like to use. It is called in a way, it's very similar to SPSS. Okay? So these days, the modern statistical program are all menu-driven. Okay? In these menu-driven programs, you have choices for data analysis. When you click on statistics, it will give you the menus. And then you click on descriptive statistics, and then it will spit out all these column size, range, maximum, minimum, skewness, kurtosis, etc., etc. So all these parameters will come out. And you can do the same thing with SPSS. So the measures of central tendency, that's the mean, median, and the mode. Okay? Now these are basic definitions, and everybody, I think all of you that have taken the statistics course would have already learned that. The measures of the dispersion, okay, the range, standard deviation, the kurtosis, and the skewness. Okay. The kurtosis means that the high kurtosis distribution has a sharper peak and longer and flatter tails. The low kurtosis distribution has a more rounded peak and shorter, thinner tails. Okay. And skewness refers to the symmetry of the curve, whether it is skewed to one side, the left, or the right. Okay, now this is the graphical presentation. Okay, so this is the normal distribution. Okay, and in the normal distribution, the mean and the mode and the median are all the same. Okay, they all coincide at the highest point of the peak. Okay. Skewness is 0 for the normal distribution. Okay. And the standard deviation and is based on the normal distribution. So the one standard deviation on both sides would include 68% of the values, and two standard deviations from the mean on each side would encompass close to 95% of the population. And what is inferential statistics? It's about making inferences about the parameter of the population. The inferential statistics, make inferences and conclusions about the population and groups based on the descriptive statistics. Now, so for example, we have a population A and population B here, okay? And we want to draw a conclusion. We take samples from a population A, okay, and we see all these little letter A's. From population B, we all see all these little letter B's. Okay, so we conclude that population A and B have different colors. Okay, so how do we know that? It's based on the sample from which we draw from. Okay, so how do you know that this is a true representation of this population A? And that is entirely dependent whether, in the process of collecting a sample, whether that process is random. Okay? If your process is not random, okay, you look into the bag and pick only the small letter A's out, okay, then you're not, this is not a true representation of the whole population, then your conclusion is wrong. Okay? So bias in the sample selection here is the key. So when we do tests to compare two populations, okay, whether we do a one-sided comparison or two-sided comparison, okay, that choice need to be based on prior knowledge. Okay, unidirectional or one-sided comparison. Okay, for example, cancer cells were incubated with drug A for the control media, and the number of viable cells were then measured by the MTT assay. Okay. You all know what the MTT assay is? Some of you have already done that. Okay. So the MTT assay is a formazan dye analysis that the cells that are alive would be able to convert that dye into a color, substance with color. You measure the absorbance of that colored substance, and that concentration of that colored substance would represent the number of live cells in the tissue culture. So with that, okay, you're asking the unidirectional analysis. You're asking whether drug A has no inhibitory effect on the viability of the cancer cells after incubation for 48 hours. Okay. So your null hypothesis is that no inhibitory effect. Okay. So it is a one-sided question because you're only asking whether the optical density of the MTT assay is going to decrease. You're not asking whether that is different or not, you're asking whether it's going to decrease. Okay. So the alternative hypothesis is that drug A decreases the viability of cancer cells. That is the optical density value of the MTT assay after incubation for 48 hours compared with the control media. Okay. So compare and contrast this one-sided analysis with the bidirectional analysis, the two-sided analysis. In the two-sided analysis, you're assuming no information about drug A, what drug A would do to the cancer cells. So you don't know. Okay, all we know is a drug. Okay, it can very well stimulate the growth of the cancer cells, or it can be inhibiting the growth of the cancer cells. We do not know. Okay, so the null hypothesis is that drug A has no effect on the cancer cells after incubation for 48 hours. Okay, and then if we have the data, if the p-value would reject the null hypothesis, then the alternative hypothesis is that the drug A affect the cancer cells after 48 hours compared with control media. Okay, so at this point, we don't know whether the increase or decrease. Okay, all we know is it's not the same. Okay, so you really need to look at the data and see which direction this difference is to report it, whether it's going to increase the growth of the cancer cells or inhibit the growth of the cancer cells. So this is the difference between a one-sided and a two-sided question. So p-value. P-value is important. Okay? So which means that I am 95% sure. Okay? And this is the usual convention that scientists accept that the p-value would estimate the probability of the results that would occur by chance alone if there's truly no difference or association. Okay? So if a p-value is less than 0.05, means that there is less than 5% chance. If it's less than 0.01, then it's less than 1% chance. So there's so-called types of error. Okay? So the type 1 error. So type 1 error is the type that we have talked about. Okay? When the truth is that there's no difference, and the test is saying that it is different, that is a type 1 error. And that is the alpha, is the probability that a type 1 error has occurred. And by convention, we pick the 5% as the cutoff value. Okay? And then now here I'm going to introduce the concept of a type 2 error. A type 2 error means that, in fact, when there is a difference, but your test did not show a difference. Okay? And this is called the type 2 error. And the probability of the occurrence of a type 2 error is called beta. And 1 minus beta is called the power of your test. And it's important that when you do a test, okay, and it did not show any significant differences, then how sure are you that you have not missed any real differences? That's when the alpha that's when the beta comes in. Okay, so the probability of the type 2 error by convention we accept at the 0.2 level or 20% level. Okay, that means that we accept the studies or have a power of 80%. Now, if you have done an experiment comparing groups A and B, then you have gotten a alpha that is greater than 0.05. That means you don't have a statistically significantly different. Okay? But your beta is also very large. Okay? It's greater than 0.2. Then no real conclusion can be drawn. You basically have wasted your time. Okay? So you can neither say that A is different from B, nor can you say that A is not different from B. Okay? So in this situation, you have wasted your time. So you have to repeat the experiment, larger sample size. Okay? That is why it's very important to calculate what sample size do you need ahead of time. Okay? So that you do your experiment and do it once, do it right, and get it done. Otherwise, you're wasting your time. Now, what is the statistical power of the study? Okay. Power, beta, alpha, sample size, okay, that I have just talked about. Now, if I do not find any difference, then how sure am I that there's no difference? Okay. So that is the key question. And this is especially important in animal protocols. You have a statistical justification of how many animals per group that you're going to use. Okay? Because you need to plan ahead of time, you need to order the animals, okay? And you plan the experiment correctly, do it once, and do it right. And same thing with clinical trials. Okay? The patients are risking their lives very often to try to learn new knowledge. And the statistical justification of how many patients you're going to recruit for the study is very important. So to calculate sample sizes, okay, I think SPSS has a module or special package that you have to pay extra to get. But on the internet, there are many sample size calculators available. Okay, and this is one of the websites that I frequently use. Okay, it's free. So for z-test, t-test, ANOVA, simple regression, proportional hazards, logistic regression, all types of different analysis. Okay? You can use these online calculators to calculate the sample size. And I find that this is very useful in planning research and planning experiments. Now we come to the multiple testing problem. So we set a p-value threshold, for example 0.05, that we say that there's a 5% chance that the result is a false positive. So in other words, although we have found a statistically significant result, in reality there's no difference in the groups means. So 5% is acceptable for one test. Okay? If we do lots of tests on the data, then this 5% can become a large number, can result in a large number of false positives. But for example, if there are 200 spots on the gel, and you apply the ANOVA t-test to each, then you would be expecting that you get 10 false positives by chance alone. Right? You have a 5% chance of false positive, that's your alpha. Okay? So 5% times 2 different tests, then you get 10. So if you do the comparisons often enough, you're going to get false positives. So how do you correct for that? You change the level of confidence to accept to reject the null hypothesis. Okay. So how many different hypotheses are being examined? How many comparisons are needed to answer this hypothesis? Okay. Are any interim analysis planned? Okay. So these questions are the issues that would affect what level of significance that you should choose as the cutoff to reject the null hypothesis. Okay. How many tests will be run in total? For example, when you're dealing with a microarray experiment, you are talking about 50,000 genes. You're running 50,000 statistical comparisons. So when you're doing just a few, 10 or less, or I mean, that's no issue, no big deal. But when you're dealing with 500,000 tests, that's a big deal. So how do you control for this issue? The level of significance in the test. If you assume that the total of the alpha is the desired type 1 error of the false positive for all the comparisons. If you have one test, then the alpha is equal to alpha total. There's no question. But if you have multiple tests and multiple comparisons, okay, the alpha total is the summation of the alpha of the individual tests, and that is going to be greater than the alpha total. So the conservative approach is to divide the alpha total by the number of comparisons. And that's the most conservative approach. Okay. So for this type of issue, the statisticians have gone in great detail into what's the best way to deal with this situation. And there are basically four common methods that are currently used to deal with this issue. And if you look at the published literature in the biomedical field, you would see that most people use the Bonferroni correction for multiple testing. And for interim analysis, the O'Brien-Fleming boundary or the Mann's analog method can be used to determine the alpha for the individual evaluations. The false discovery rate control is the statistical method to control for these multiple comparisons. Okay. It is designed to control for the expected proportion of incorrectly reported null hypotheses or the false discoveries. So the Bonferroni correction is a pretty stringent type of control, and it's the methodology falls into the family-wise error rate procedures. Um, but when we're dealing with the microarray experiments, so many tests are being performed. If you apply the stringent type of correction for false discovery, the hits, the number of hits becomes very few. Okay? So therefore, as opposed to the expected proportion of false discoveries, because to increase the amount of information that we can dig out of the array experiments, we have to compromise to have a greater power at the cost of increased rate of type 1 error. So therefore, people have proposed new methods of false discovery rate control methodologies to apply for these genomics or proteomics or transcriptomics, all these omic type of experiments in order to compromise the at the cost of increased rates of type 1 to improve the power of the discovery, to identify more information, to get more out of these microarray tests. So what tests do I use? That is very often the dilemma that we face given a data set. Okay? So we have a set of data, and okay, so we want to find out whether the group B are different, or the or group C is different from the control or whatever. Okay? What test should I use? Okay, so I'm going to stop here for a little bit and let everybody have a bathroom break. Okay, so we'll come back in maybe 10 minutes. Let's come back in 10 minutes.
Tối qua mình đã gửi cho các bạn cái tài liệu học, thì bạn có bạn nào chưa nhận được thì liên hệ bạn điểm danh để gửi lại email cho các bạn. Các bạn kiểm tra xem thử là mình đã nhận được email của ban tổ chức có gửi cái slide bài giảng cho một thông báo nữa là từ bữa học sau là các bạn sẽ điểm danh vào giữa giờ chứ không phải là vào giờ. Các bạn chỉ điểm danh một lần vào giữa giờ.
Squeeze the system to try to implement.
Okay, let's get started again. Okay, so yeah, uh, what tests do I use? That's the most often question that we face when we have a set of data. Uh, First, we need to know what type of data is being presented. Uh, how many groups are there? Are the data normally distributed? And are the data points interrelated or independent? This is a program that I use called Sigma Plus. Okay. And it's menu driven just like SPSS. In these tests, okay, you import your data set, and if you have a data set recorded in Excel, they have functions that you can import the data, or you can even just simply cut and paste data into the spreadsheet of this particular program. I think it's the same way with SPSS, that you can even open from within SPSS, you can open Excel spreadsheet files. And after you open your data set, then you can choose what descriptive data analysis, as well as the different comparisons to how to access the data. So in this particular program, they ask you whether you're comparing two groups, or you're comparing many groups, or you're doing other types of analysis like survival analysis, or regression analysis, or correlation analysis, etc. So this is a view of the SPSS. So with SPSS, you click Analyze, and you come to Compare Means. Within Compare Means, you have the choices of t-test or one-way ANOVA, paired sample t-test. That means if the samples are paired and is not independent. So the first four questions that I asked in that here. So if you figure this out, then you have no problem picking the right test in the programs. Okay. So based on the answers to those four tests, you will be able to correctly pick the test to use. But okay, if you have a data set that fail the normal distribution. Okay. So remember what I said earlier, that the assumption for the t-test is that the populations that you're comparing follows the normal distribution. Right? If your sample failed the normality test, that means that your populations were not normally distributed. Then you cannot use the t-test. Then you need to use the non-parametric tests. So among the non-parametric tests, then you have whether the samples are independent or related samples, etc. Then you pick the right test from within. So within the Excel spreadsheet, you can do the t-test. Okay? To do the t-test, all you need to learn is the formula command for the t-test. But within Excel, it does not help you in terms of doing any tests or to tell you whether this is the appropriate test or not. Okay? If you want Excel to do the t-test, it will do the t-test for you. But it does not tell you whether it's the right test or wrong test. It just gives you some. It is your job to decide whether that is the right thing or not. The student t-test and command in the Excel is the t-test, parenthesis, and then you describe the data ranges, and then these. Okay, so this is the cells that are containing the data from sample 1. These are the cells containing the data from sample 2. That's whether the test is a one-sided test. Okay. And the type of test, whether it's a pair test, or independent equal variance test, or independent unequal variance test. Okay. So Excel is capable of doing the t-test, but you're doing that at your own risk because it does not give you much help. Okay, you must know exactly what type of whether t-test is appropriate, and whether and which type of t-test is appropriate. Okay, if you don't know, then perhaps other computer programs will be able to provide you with more guidance. For example, here for this program called signal plot, okay, you say here two groups. Okay, you pick two groups, and then it will perform the normality test automatically. Okay, if it passed the normality test, then it will go on, and it will test the equal variance test, and whether it's passed or not. Okay, so basically in this program, it will do the normality test and variance test to help you to pick the right kind of t-test. Okay, so remember in Excel that you have to know which one to use in order to specify that in your command. And then it will do the t-test and then give you a brief explanation of what the t-test means. Okay, so if the normality test fails, or if the equal variance test fails, it will help to direct you to a different test that is more appropriate for your set of data. So for SPSS, okay, and you take compare means, and then you decide, depending on whether you do the independent test or pair t-test, etc. Okay, or if you're dealing with multiple groups, more than two groups, you should not use t-test. You should use one-way ANOVA. With SPSS, okay, it will check whether there are missing variables. So check the variables, check the criteria, the confidence interval, 0.95%. Okay, so then give you the statistics, and it'll tell you what the confidence intervals are, what is the sigma and the two tails of this test. Okay, and in this case, it's not significantly different. So after you've done the test, okay, so now you want to present your data in a paper in your journal. Okay, so when you plot the data using this is sigma plot. Okay, so when you do this, a lot of times the programs would have the default parameters to show when you plot the data. Okay, this is how it looks when it comes out. So you can change what the Y data is to relabel them. Okay, so one good way to present the data distribution of a population is to use the box plot. I like the box plot a lot. So with the box plot, it gives you the median, the 25 and the 75% confidence limits, and the 90% confidence and 10% confidence limits, and the outliers. So with the default output, okay, even if you change the labels, it does not look good. Okay, when you cut and paste it to a paper, it does not look very pleasing. And also that a lot of times the papers are very restricted in terms of the space, and very often your figures would need to be shrunk. Okay. Look at how thin these lines are. Okay. If these figures are shrunk, the line would very often be not very clearly visible. So that here is an example of how I would edit the default output of these graphical programs to have a good graphical presentation of your data. One thing is that you need to make sure the lines are thick, okay? So that after the figure is shrunk, the lines are clearly visible. Okay? Because many of the reviewers of the papers are old people like us, and we are we have presbyopia and cannot see thin lines very clearly. And the fonts and the labeling need to be with bold, big, heavy fonts. Okay? And also that there's, if use of color is appropriate, use color to emphasize your point. Here, for example, I've added the, for box plot, the default output, the line in the middle here is the median. Here I've added the mean. Okay? So as you can see here, the mean and the median are very close to each other. So this population is has distribution is very close to the normal distribution. Okay. But for this population, the median and the mean are quite far apart, and this population is skewed. So with the graphical presentation like this, one look you can see whether the t-test is appropriate or not. Okay. So this population, yes, normal distribution. This population, maybe, depending on how big your sample is and how reliable this separation is. Okay, if this is a large sample and you see a skewed distribution like this, then you know for sure that this is not a normal distribution and the t-test is not appropriate. So another frequent way of presenting the data is the bar chart. And this is the default bar chart output. And again, like for the purpose of publication, you need to change the default output to graphs that have heavy, strong lines so that it's clearly visible when it's shrunk, and large lettering and labeling so that it's clearly visible after it is shrunk. So normal versus skewed distribution. Now, the normal distribution test has failed, and the t-test is not the appropriate test. Then you need to use the non-parametric statistical tests. So parametric statistical tests can be used to assess variables that have a normal or symmetrical bell-shaped distribution on the histogram. For non-parametric statistical tests can be used to assess variables that are skewed or non-normal. So you can look at the histogram to decide. For myself, I like to look at the box plot. That would give me a good idea about that. Many statistical programs will test the normality when you request the test, and the test that assume normal distribution. For example, test. The program that will recommend alternative tests if the data fails the normality test. Okay. So blindly assuming normality can lead to wrong conclusions. Okay. So one thing about the SPSS is we need to be careful that it does not do this automatically. So it does not perform the normality test automatically. So you need to take a look at distribution of the data before you decide to pick the t-test in SPSS. So one of the non-parametric tests that you use when the population fails on normality is the Whitley-U test, similar to the Wilcoxon-Rank sum test. It's used in place of students' t-test for skewed data. It's a non-parametric test and used to rank the value instead of the actual value. It's a univariate. It tests the difference. It's unmatched. It's continuous quantitative data, non-normal distribution, and compare two groups. Now, whether to pick unmatched or matched test is another question. Some statistical tests that are designed to assess groups that are matched, unmatched, or independent. Like for example, if we look at the glucose difference between men and women, okay, and each of these glucose readings are from different people. Okay, they are completely independent. And a different question, like if we frame it, for example, is the blood glucose different between baseline and after treatment? Okay, from the same person. Okay, you're comparing the before and after. And that same person is the link between the data. And therefore, these the paired t-test, or some of these tests that are for matched or paired samples would be more appropriate than the independent tests. So the paired t-test is used to compare the average or measurements made twice with the same person, or it used to compare a different group with a matched control group. Right? So a matched control group meaning that there are some characteristics in the control group that are matched to the particular experimental sample. And for example, did the procalcitonin level change significantly from the presentation of sepsis in the emergency room to admission to the ICU? We're talking about the before and after, the values from the same patient. The univariate test that we're looking at the difference of the means, the matched samples, the continuous quantitative data, because it's a t-test and it has to be normal distribution and this comparison between two groups. And the Wilcoxon-Stein rank test to compare two skewed continuous variables that appear or match. Like for example, such a one question would be, was the Glasgow coma scale score different between the scene and the emission? Okay. So Glasgow coma score is a score that evaluates how unconscious the patient is. And the scene, this refers to the scene of the, for example, motor vehicle accident. Okay. And the motor vehicle accident scene, the patient was stunned, unconscious, and this scale measures how unconscious the person is. Okay. And this is a repeat measurement when the patient goes to the intensive care unit. Okay. This is comparison to see whether the patient getting better or getting worse. Okay. So it's comparison of the score. Okay. The same person. So these the data is matched. It should be a matched comparison of the data from the same person. So it's a univariate analysis comparing the differences, matched data, it's quantitative data, and it's non-normal distribution, and it's comparison between two groups. This is an example is a very common mistake. This is the use of a t-test to compare the means of two groups in an experiment that consists of 3 or more groups. And for example, here is an experiment that have 4 groups of animals. Okay. So this is a group of animals that has a wild type leptin receptor. This is a group of animals that have the leptin receptor mutation and they're homozygous. And these mice are diabetic mice. They are have a severe insulin resistance, and this is a set of data that representing about the serum measurements of the serum insulin levels from these mice. Okay, and this is a bar chart of all these different groups of mice. Okay, so all these 3 are the diabetic mice, and these 2 groups. This group was treated with a drug called metformin. This one was treated with a drug called rosiglitazone. In these drug-treated mice, the insulin resistance improved, and the circulating insulin would drop. Right? So these data demonstrate that these drugs are effective in lowering the circulating insulin level. Okay, so with these bar charts, the error bars represent what? The error bars represent, you have to look at the individual paper. Okay? So very often, people would just use standard error, or some people would use standard deviation. Okay? I personally would use 95% confidence interval. Because if you use standard error or you use the standard deviation, you need to know how big the n is. What is the n? What is the size of the sample from which the data is obtained in order to know what the 95 confidence interval limits are. Okay? If we already done all that, taking the size of the sample into consideration and computed the 95% confidence interval, then it would be very easy for the reader to see, just to see whether the 95% confidence interval would overlap with the mean of any of the other groups. Then just from one look, you can tell whether that difference is significant or not. Okay. So, although out there in many journals, the R's, you can use it to represent standard deviation, standard error, whatever you choose. I personally prefer the 95% confidence interval. Now, here you have this experiment, 1, 2, 3, 4 groups. If I want to say that this group is significantly different from this group, okay, t-test is not the appropriate test because the experiment is done with 4 groups, not 2 groups. Okay? So in this situation, you need to use the one-way analysis of variance. Okay? So the one-way analysis of variance looks into all 4 groups to see if there's any significant difference among these 4 groups. And then after that, this so-called the post hoc comparison, post hoc intergroup comparison that you can use either a 2-key test or Dunnet test, several tests that can be chosen to compare among the groups. Okay, so the intergroup comparison. Okay, so you can compare this group with this group, compare this group with this group, or compare this group with this group. Okay, so the p-values reported should be the p-values for the post hoc intergroup comparison of the one-way analysis of variance. Okay. So that is the appropriate test for this situation, and you will find this mistake over and over again in the published literature. So if this is the signal plot program. Okay, in the signal plot program here, if you choose compare many groups, it will show you what to choose. One-way ANOVA, two-way ANOVA, three-way ANOVA, etc. Okay, so the difference between, one-way ANOVA is the basic one that we used in the previous example. Okay, so two-way ANOVA and three-way ANOVA are more advanced statistics that I don't have time to get into that at this point. So ANOVA, one-way ANOVA is used to compare 1 and 2 means from independent groups. Okay? So if you're asked a question, is the age different between the white, black, Hispanic patients? Okay. So like in America, we have many different races, and that it's more than more than 2 groups. So when you do that comparison in your study sample, comparing the mean age among the groups, then you have more than 2 groups, and that would mean that you would need to do analysis of variance. Now, two-way ANOVA is used to compare the more than 2 means by 2 factors. Okay. So, for example, this is the 2 factors that we're talking about, whether they have the factor of sex or the factor of having pneumonia or not. Okay. So, for example, you can ask, is the age different between the males and the females, with and without? So in that situation, you would use the two-way analysis of variance. For continuous variables that are not normally distributed. Okay? So the one-way ANOVA, just like the t-test, assumes the populations are normally distributed. Okay? If the distribution is not normal, you cannot use the one-way, and you would use Kurz-Coleman's one-way ANOVA, which is the non-parametric test. This non-parametric test for the one-way ANOVA. For example, it's the length of stay in the hospital that are different by ethnicity, different races. Okay, the length of stay in the hospital usually is a non-normal distribution. So when you analyze non-parametric tests with more than 2 independent samples with a not normal distribution, that's the situation. when we apply this test. Repeated measures, okay, similar to the t-tests. They have the matched situation, the matched data situation. Okay. For ANOVA, you also have the repeated measures situation. That, like for example, if you have a before and after uh, type of data set, and you can apply this. You still assess the change in two or more continuous measurements made on the same person. Can compare groups and adjust for covariance. Okay. Do changes in the vital signs within the first 24 hours in cancer patients predict which patient will develop sepsis? Okay. This would analyze the use general linear model for the repeated measures. In many of the papers that you see, okay, like for especially in clinical studies, you would have the patient characteristics and you have the patient groups, okay, and then you have the number of patients that fall into each group. Okay. When you compare these groups, okay, you're looking at these distribution of proportions. How many patients fall into each category, and what percentage does that represent in each as a whole? For this type of data, this type of percentage data or proportion data, we would use tests such as the chi-square test. Okay. This is perhaps the most commonly used statistical test. It tests whether two or more percentages are different. For example, suppose that a study of 933 patients with cancer, and 10% of the men, that is 44 patients, of the men developed pneumonia compared with 5% of the women that developed pneumonia. Okay. So the men and the women, okay, these percentages significantly different. Okay. So what's the probability that this observation was by chance alone? Okay. So this chi-square test is a univariate test. Look at the difference in the proportions. It's unmatched, and it's looking at the nominal data, meaning that this is a grouping, and is more than or equal to two groups. Okay, for the types, we have to validate the number of individuals within each group need to be greater than or equal to 20. Okay, so what if that greater than or equal to 20 requirement is not satisfied? You can use this Fisher's exact test. This test can be used for 2x2 table when the number of the cases is too small to satisfy the assumption of the chi-square. That is, the total number of cases is less than 20 in any of the categories. I'm sorry, the total number of cases is less than 20, or the expected number of cases in any cell is less than 1, or more than 25% have expected frequency less than 5. So another type of data that we encounter would be a correlation. I'll give you an example here that the Ki-67 index. Okay. Have you all heard of Ki-67 index? Okay. The Ki-67 is a gene, a protein that is expressed in the nuclei of proliferating cells. So if you do immunohistochemistry chemical staining, immunohistochemical staining of the Ki-67, so the nuclei that stain positive represent cells that are proliferating. Okay, so if you take a piece of tissue of a cancer and stain for Ki-67, the percentage of the nuclei that stain positive for Ki-67 would represent the percentage of the cancer cells that are actively growing or proliferating. So, in other words, the Ki67 index is the percentage of the nuclei that stain positive for the Ki67, and this represents the percentage of the cancer cells in that piece of tissue that are actively growing. Here, PDPRO, okay, is another gene that is a tumor suppressor. So if you stain the tissue for the presence of this tumor suppressor, okay, how much of that protein is present? Okay. So you ask the question, is the presence of this tumor suppressor protein associated with a decrease in the Ki67 proliferation of the cancer cells? Okay. So when you ask this question, what's the best way to demonstrate the point? As well, when you have more tumor suppressor present in the tissue, the slower it runs. How do you demonstrate it? So you stain the tumor tissue for the Ki67, get the Ki67 index, okay, and then you stain the tumor suppressor, okay, and you have a score of the staining demonstrating the amount of the tumor suppressor present, okay, and then you simply plot them on an XY plane. And then from this distribution of the data points, you ask whether there is a linear relationship between these numbers. Okay. So to answer the question, okay, so you assess the linear association between two continuous variables. So this test is called Pearson correlation test. And if you have a R coefficient value, it will represent, if R is equal to 1, it will represent a